Hello, everyone. Thanks for attending this talk. My name is Young, and I introduce my micro paper on AutoScale, which is energy efficiency optimization for stochastic edge inference using reinforcement learning. This work was done with Professor Kerojin Mu when I was in the Arizona State University as a postdoctoral research associate. Recently, as you know, most IT companies are providing intelligence services such as object detection, speech recognition, and personalized recommendation. These intelligence services are using deep neural network as the key machine learning components. While training of deep neural network is usually run on the data centers due to its compute and memory intensive nature, there have been increasing pushes to run neural network inference at the edge in order to improve response latency by removing data transmission overhead, to reduce burdens on networks as well as data centers, and to exploit features only available at the edge. For edge inference, we can exploit various on-device processors such as CPU, GPU, DSP, and NPU. Additionally, via wireless networks, we can also exploit connected systems such as cloud servers or another locally connected edge device like tablet. These execution targets are getting even more diverse as a recent work from Facebook showed that there are more than 2,000 types of mobile SoCs. The execution targets can also be augmented with DVFS quantization and batch execution. As there are various execution targets available for the edge inference, it is crucial to select an optimal execution target. Then, which execution target would be the optimal one? There are three important optimization axes for edge inference. First one is energy efficiency as the edge devices are energy constrained. Second one is latency, since users abandon the service if its latency exceeds the acceptable limit. Third one is inference accuracy to achieve human-level accuracy. In summary, the optimal execution target should maximize the energy efficiency while satisfying the latency and accuracy constraint. However, finding the optimal execution target is challenging due to the unique characteristics of edge cloud collaborative execution environment. To see the challenges for the optimization of edge inference, I show the real system characterization results and introduce optimization opportunities for the edge inference. In fact, finding the optimal execution target for edge inference is challenging because the optimal target depends on various features such as system profiles, neural network characteristics, and stochastic runtime variance such as on-device interference and wireless network signal strength. Let's see one by one. First of all, the optimal execution target depends on the edge cloud system profile since mobile SoCs are highly fragmented. This figure shows the inference latency and energy efficiency of edge inference. The gray and pink bars indicate the inference latency and the energy efficiency respectively, and the dotted line in the middle of the bars indicate the QoS target. In case of high-end device, on-device DSP is the optimal execution target since its performance is high enough for the inference execution. On the other hand, in case of mid-end device, cloud server is the optimal execution target since the performance of on-device processors is not sufficient for the inference execution. This makes the optimization of edge inference really difficult since there are more than 2,000 types of mobile SoCs as a recent work from Facebook showed. In addition, even in the same device, the optimal execution target can vary depending on the neural network characteristics. This figure shows the cumulative latency of layers in two neural networks, which are Inception version 1 and MobileNet version 3 for each column. In each column, the x-axis shows the on-device processors and the y-axis shows the latency. The brightest parts in the bar represent convolutional layers and the darkest parts represent fully connected layers. And the rest parts represent other layers such as pooling layers. As shown in the left column of the figure, convolutional layers run more efficiently on coprocessors such as GPU and DSP rather than CPU. On the other hand, as shown in the right column of the figure, fully connected layers run more efficiently on CPU rather than the coprocessors. Finally, the optimal execution target ships with stochastic runtime variance such as on-device interference. In a real use case scenarios, there can be several applications concurrently running along with the inference because recent mobile devices support multitasking features such as screen sharing between applications. For example, web browser or music player can run concurrently with the inference execution. Since those applications usually have varying computation and memory resource utilization, the interference from the application significantly affects the optimal execution target. Let's see an example. When MobileNet version 3 runs on a high-end device and there is no application concurrently running with the inference execution, the optimal execution target is on-device CPU. However, when there are concurrently running applications and the applications perform CPU operations, the energy efficiency and the performance of CPU are significantly degraded due to the CPU resource contention. In this case, the optimal execution target shifts to the GPU. On the other hand, when the applications perform memory operations, the energy efficiency and the performance of on-device processors are all degraded due to the memory resource contention. In this case, the optimal execution target shifts to the cloud. The optimal execution target also shifts with network signal strength, as the wireless signal strength can significantly vary in daily life because of various reasons such as user movement or the network environment. When ResNet 50 runs on a high-end device and the signal strength of all wireless networks are strong, the optimal execution target is the cloud server. However, when the Wi-Fi signal strength gets weaker, the energy efficiency and the performance of cloud execution are significantly degraded due to the increased data transmission time. In this case, the optimal execution target shifts to another locally connected edge-like tablet. However, if the signal strength of near communication networks such as Wi-Fi Direct also weakens, the energy efficiency and the performance of the connected edge are also degraded. So the optimal execution target should shift to the on-device DSP. Because of the complex design space due to stochastic nature of edge cloud execution environment, simple predictive techniques are not sufficient for the optimization of edge inference. This figure shows the energy efficiency of baseline of edge CPU. Predictive approaches such as regression-based approaches, classification-based approaches, Bayesian optimization, and the optimal scheduler. The y-axis indicates the performance per watt of the techniques. As shown in this figure, there is up to 5x gap between the predictive approaches and the optimal one. This means that the complex design space of edge inference optimization calls for the need of novel technique which can accurately select the optimal execution target. Because of the importance of edge inference domain, many previous works have tried to optimize the edge inference execution. At the beginning, many works have focused on cloud execution because of the compute and memory intensive nature of deep neural networks. As the mobile systems become powerful, many techniques try to partition DNN inference execution between the cloud and the local mobile devices. Also, there have been many techniques which try to optimize DNN inference by partitioning it among various on-device processors. These previous works are mostly built upon regression-based approaches, so there still exists 5x room for energy efficiency improvement. From now, let me introduce the proposed design called AutoScale. As shown in this page, for the given stochastic edge cloud execution environment, AutoScale selects the optimal execution target adapting to various features with reinforcement learning. To do so, AutoScale takes the various features as inputs and chooses execution target as the output. For the reinforcement learning algorithm, it is important to custom design the value function which calculates the score of each execution target, state which models various environmental features, action which corresponds to control knobs of the systems, and the reward which models the optimization objective. To custom design the reinforcement learning algorithm for the edge inference, we first use the lookup table for the value function as its table lookup overhead is low enough for the edge environment. We then define states with the various features and defined actions with the available execution targets for edge inference. The actions can be augmented with DVFS, quantization, and batch execution. Finally, we define the rewards with the results observed during the execution of the selected execution target. For the detailed reward function, please see the equation 5 in the paper. Before the reward value is converged, AutoScale self-learns the policy to select the optimal execution target. AutoScale first identifies the state based on the edge cloud execution environment. For the identified state, AutoScale finds an action with the highest Q value based on the Q table. After that, AutoScale estimates the energy consumption, measures the latency, and obtains the accuracy for the selected action. Based on the observed results, AutoScale calculates the reward, which indicates the distance from the optimization objective. It then updates the Q table based on the calculated reward. Let's see how AutoScale learns the optimal execution target. Suppose a high-end mobile device runs MobileNet version 2. Based on the features, AutoScale identifies a state. For the state, AutoScale selects Edge CPU as the action since it has the highest Q value now. It executes inference on the Edge CPU while observing its results. Based on the results, it calculates the reward and updates the Q table based on the calculated reward. After that, for the same state, AutoScale selects Edge DSP as the action since it has the highest Q value now. It executes inference on the Edge DSP while observing its results. Based on the results, it calculates the reward and updates the Q table. Once the Q values are converged, AutoScale always selects the action which has the highest Q value. AutoScale adapts to neural network characteristics by identifying different neural networks as different states and learns the optimal execution target for the identified state. And it also adapts to runtime variance by identifying different states and learns the optimal target for the identified state. From now, let me explain the evaluation results of the AutoScale. For the evaluation, we used 10 state-of-the-art neural networks as shown in this page. For the Edge Cloud collaborative execution environment, we used 3 edge devices with different performance, 1 tablet connected with Wi-Fi Direct, and 1 server connected with Wi-Fi. For the power measurement, we used Monsoon Power Monitor. To emulate stochastic runtime variance, we used real-world applications such as web browser and music player for on-device interference, and random signal generation with Gaussian distribution for signal strength variance. AutoScale significantly improves energy efficiency of edge inference compared to baseline, satisfying QoS targets as much as possible. This figure shows the QoS guarantee ratio of various techniques. The x-axis shows the techniques and the y-axis shows the QoS guarantee ratio. As shown in this figure, AutoScale significantly improves QoS guarantee ratio and shows similar QoS guarantee ratio with the optimal one. This figure shows the normalized performance per watt of various techniques. The x-axis shows the techniques and the y-axis shows the performance per watt normalized to the baseline of Edge CPU. As shown in this figure, AutoScale improves 9.8x energy efficiency compared to Edge CPU. Actually, its energy efficiency is almost close to the optimal one. This is because AutoScale accurately selects the optimal execution target even in the presence of stochastic variance with reinforcement learning. This figure shows the prediction accuracy of AutoScale compared to the optimal scheduler. The x-axis corresponds to the execution environment, and the y-axis indicates the prediction accuracy of AutoScale. As shown in this figure, when there is no stochastic variance, AutoScale shows 97.9% of prediction accuracy on average. In addition, even in the presence of stochastic variance, AutoScale shows more than 96.8% of prediction accuracy, which is high enough for the edge inference optimization. Other results show that even in the presence of runtime variance, AutoScale improves energy efficiency by 10.7x over the baseline. In addition, AutoScale continues improving energy efficiency subject to different accuracy targets. Finally, we found that learning transfer improves conversion speed of reinforcement learning, reducing learning overhead by 21.2%. For more details, please see the paper. Let me conclude this presentation. This paper provides an in-depth performance and power characterization of neural network inference through Edge Cloud collaborative execution considering various features. Based on it, this paper proposes AutoScale, which is built upon reinforcement learning to accurately select the optimal execution target in the stochastic Edge Cloud collaborative execution environment. Real system implementation and evaluation demonstrate that AutoScale improves energy efficiency by 9.8x on average over the baseline setting, satisfying real-time performance and accuracy constraints. We believe AutoScale is a viable solution and will pave the path forward by enabling future work on energy efficiency improvement for edge inference. This is the end of my presentation, and for the open source of AutoScale, please refer to the link shown below. Thank you.